Hello guys, welcome to Rasayan Academy all of you. So we move onwards to another video on name reactions. Guys, today we are going to talk about the reactions including nitrene as the intermediate. Alright, so you can say including nitrene as an intermediate or including isocyanate as an intermediate. Alright, these are also very important reaction, very basic, and also have been asked in each and every of these competitive exams, the CSR net, GATE, TIFR, IIT JAM, everywhere. Alright, so let's study these easy name reactions, which are also sometimes very confusing and very difficult to remember. Alright, so let's discuss all of them. So first thing guys, we are going to study the HOFMANN rearrangement, Curtius rearrangement, Schmidt rearrangement and Lossen rearrangement in this session, in this video. And we have already done the Beckmann rearrangement and the abnormal Beckmann or the Beckmann fragmentation. We have already done that, and I will paste a link of that video also, so that you can see and compare. Equally important for your examinations. Okay, so yes, let's study first reaction, Hoffmann rearrangement, sometimes also known as Hoffmann bromamide degradation. Okay, yes. So what is Hoffmann rearrangement, guys? Treating primary amines with hypohalites. Alright, so hypohalite is basically, let's say if we are taking this combination bromine and NaOH, hypohalite is OBr minus. Alright, that gives you primary amines with one less carbon, and that is why we call it degradation through isocyanate intermediate, right? Very simple reaction. Let's see the mechanism. So you are starting with the amide, okay? Let's say you have a amide molecule like this in the presence of bromine. Now see the condition, primary amide should be present. You cannot take a substituted amide in this particular reaction. Why? Because you need both of these hydrogens. We will see how. First of all, you are taking bromine in NaOH. What is it going to do? Bromine is going to be attacked by the nitrogen, and also in the presence of NaOH, the OH minus can take away one of the protons, give a negative charge on the nitrogen so that the bromination becomes easy. Alright, so for now you are going to have the N-bromoamide like this. Alright, now the proton becomes even more acidic when it is connected to a nitrogen which is connected to electronegative atom bromine, easily removed by the OH minus, gives you this kind of a carba and this kind of a anion or nitrogen. Okay, so guys, there are two types of mechanism that you can do from here. One is very simple. You are just going to, let's say, break this Br minus bond from here. So Br minus is eliminating. Okay, let me show this with a different pen, because this is, we are moving into a different mechanism over here. So you have got the nitrene. If the Br minus eliminates, the nitrogen having this negative charge will turn into a electron pair. It is no more a negative charge. Okay, so this is your nitrene molecule. And you can do the rearrangement to get the isocyanate, which I have written over here. This is your isocyanate intermediate. Okay, so isocyanate intermediate has been observed, but it is not necessary that in all the molecules you get the nitrene. Okay, so what if we are not getting the nitrene? How do you write this process? How do you move the arrows? Move the arrows in this way. The negative charge, alright, let me just show over here. Let me rewrite the molecule. The negative charge will fall over onto this carbon nitrogen bond. One of the group is going to migrate on nitrogen and eliminate the Br along with the same reaction. Okay, so what did I do? Just the same, the negative charge falls over this carbon carbon bond. The R group is going to migrate on nitrogen and eliminate the Br. Alright, so this is how you can write it. Sometimes it is mentioned that you get the nitrene, sometimes not. In the Hoffmann bromamide degradation reaction, the nitrene is, even if it is formed, is so unstable, it's quickly going to rearrange to the isocyanate intermediate, which we can trap. And there has been a lot of evidences that you are getting the isocyanate, right? The first and the foremost is attacked by water. you are going to first get the carbamic acid. All right. So you are going to first get the carbamic acid over here. This is your carbamic acid. Now carbamic acid is going to quickly decompose into amine and carbon dioxide, which is going to eliminate. Okay. So that is why it is known as a Hoffman bromamide degradation reaction, because here you're starting with the primary amide. You need both of these hydrogens in the mechanism, gives you primary amines with one less carbon, and CO2 is eliminated. Okay, so this is a very simple rearrangement reaction. Let's see an example over here, guys. So let's see the example number 2 first. The original conditions, bromine and hydroxide, when they are taken to a big molecule, as you can see, right? So guys, this is a big molecule. You have a primary amide. None of the other atoms are touched in this reaction condition. 0 degree centigrade, bromine and KOH. What just happens? Once again, you are just going to go through the same mechanism, conversion of CONH2 to amine. Okay? All right. The molecule is as it is, not disturbed at all. Now, what about this molecule? NBS variant. What is NBS? NBS, guys, it's not necessary in your exams that you are only going to get the bromine and OH minus. Yes, this is the basic thing. You have started the original conditions here, right? But not necessary you'll always get the same thing, right? So NBS variant is you are having NBS over here in the presence of right, in the presence of a radical initiator. Your NBS will give you bromine radical, but here we don't have any radical initiator. What is it supposed to give? It is supposed to give a bromine electrophile. Okay, like this. So let's say you are getting a bromine electrophile, still the reaction would be the same. You have NHBr over here, all right, and then what you can do is dbu is a base, so this dbu molecule can remove this proton from here. All right, once again, when it removes the proton, let's uh, let's just write till the anion, and then you can rearrange the bonds directly without even getting the nitrine. That's fine. So N minus is over here. The charge falls on the carbon nitrogen bond. This bond is going to migrate over the nitrogen, and Br minus eliminates. What do you have now? Yes, what do you have now? You have this carbon. This carbon will directly be attached to nitrogen in this way. You have a double bond with nitrogen, and this is your isocyanate that you are going to get. Okay, so this is your isocyanate molecule that you are getting. What should be the product, guys? Now you have MEOH in the system, that is methanol. So you don't have water, it's okay. You are having methanol, which means methanol is going to attack over this system, and you get the N substituted amide. All right. This is OME, okay? This is OME, methoxy. So what do you have, guys? Finally, you are having the carbamate. Okay, this is not a carbamic acid because acid will quickly dissociate, right? If there was OH over here, then it will be known as carbamic acid, but this is your methyl carbamate. Okay? Yes, this is your N substituted amide that you are going to get. This is your final product of the first example. All right, so it's not necessary that you always do the decomposition. You can provide some other nucleophile also, and then you can get the substituted carbamate also. Okay, so this was your first reaction, Hoffmann bromamide degradation or Hoffmann rearrangement. We have seen both the reactions. Now, yes, so sorry, but yes, this will be known as the degradation. A quick classification, this will be known as degradation. Why? Because the molecule is degrading. And this will be known as Hoffmann rearrangement. Okay, so yes, we need to have this clarity. Why? Because only the rearrangement is taking place, right? Okay, now we move onwards to next reaction, that is your Curtius rearrangement. Guys, very simple once again. You just have to remember what is the condition. Curtius rearrangement may you are going to start with the sodium, you're going to do the rearrangement of your acyl azide, and you are starting with, let's say, RCOCl molecule plus NaN3. Okay, so you have to remember this is your thermal rearrangement of the acyl azide, just that. So alkyl, vinyl and aryl substituted acyl azide. Okay, so any substitution is possible. The R could be anything, alkyl, vinyl or aryl, right? Acyl azides are doing the substitution. Thermal 1 to carbon to nitrogen migration with the elimination of nitrogen gas producing isocyanate. Same rearrangement reaction. Just remember, in the presence of heat you are doing this reaction. Okay, so reaction of isocyanate product with nucleophiles provide carbamates. You have just seen that the nucleophile could be water, it gives you amine. Okay, it could be methoxy or let's say alcohol to give you carbamate. It could also be NH3 to give you urea and other N-acyl derivatives we will see. Alright. Also, photochemical mechanism goes through nitrene formation, not the thermal reaction. Thermal reaction will directly form the isocyanate intermediate. Photochemical mechanism will have the nitrene. Okay. Yes. So let's see what's going on. It is your acyl azide. We call it azide. Okay. In the presence of heat undergoes rearrangement. Azide is removed now. Okay, and then in the presence of a nucleophile, now this is a protonated nucleophile, it could be your ammonia also, right? Let's say it is ammonia like this. So ammonia is going to give you the substituted urea molecule. Water is going to give you as it is your amine molecule, and CO2, that is similar to Hoffmann bromide degradation, right? Yes, because you're going through the same intermediate. Okay, very simple. Let's consider the reaction mechanism. You have first of all acyl chloride. Acyl chloride will be converted to acyl azide in this manner. Okay, so let's say this is your acyl azide molecule. Now what happens is, in the presence of heat, you can see the nitrogen elimination will take place very quickly, but then you are not supposed to form the nitrene in the thermal condition. What you are going to do is, if you just remove this bond, you will get the nitrene, but you will write it in this way. The bond falls over the carbon nitrogen bond and the alkyl group migrates on this nitrogen. Now you remove it. So you directly can write the isocyanate like this, minus N2 gas. Okay. Now whatever happens with the isocyanate is, whichever nucleophile you are giving, let's say you are giving ammonia, attacks on the carbonyl, bond opens up. So the weaker double bond, that is your carbon nitrogen double bond, it's weaker, so that is going to open up. You are getting the N alkyl urea. Okay, and if you get the water, you are going to get the amine as well as CO2 gas. All right, so let's see this example, very important example over here. So guys, you are starting with this acid. There is a very important there's a group over here. It's the peroxide is attached to these two carbons, right? Very sensitive molecule. Now what are we doing? We are first of all converting the COOH into this molecule, the chloride derivative. Okay, we are first converting this into the chloride, acyl chloride derivative through this molecule. All right, ethyl chlorocarbonate. All right, now what do we have? N3 minus azide. So guys, the reaction is the same. The conditions are a little bit different, but the reactivity, the reaction, everything is the same. So you are going to get, let's say, the azide like this. Now the further reaction you can do, guys, yes, everything will be the same. Let's see what is the nucleophile now. The nucleophile is ethanol. Okay, so you can just directly write the isocyanate from here, because now you know how the rearrangement takes place. So this carbon over here is going to migrate on one of these nitrogens minus nitrogen gas. Okay, so I am just, let's say, directly going to write that there is my nitrogen, double bond C, double bond O. Okay, and then the ethanol is going to attack. It will attack over here. The bond opens up. This is your product, let's say. All right. Yes, NHCO2 ET. Okay, this is your final product. All right. So Curtius rearrangement, what you have to remember is, start from the acyl chloride and get the product based on the nucleophile. Don't remember this reaction with respect to product. All right, remember this reaction with respect to the condition. Sodium azide you are taking to the acyl chloride, and the rearrangement in the presence of thermal or photolytic condition. In the thermal condition, you will get directly the isocyanate. In the photolytic condition, let's say what happens over here is, in the photolytic or photochemical condition, see, you have already got this intermediate. There's a negative charge on this nitrogen, positive over here. So this is going to eliminate minus N2, all right, in the presence of light, and you get the nitrene. Okay, this is what you have in the photolytic condition. Okay, now we move onwards. Next, similar reaction, very similar, that's why confusing, but not so similar, guys. Schmidt rearrangement occurs in the acid medium. Okay, so there are three conditions different. Curtius reaction occurs with sodium azide in the thermal condition. No acid and base is required. Schmidt rearrangement in the acid catalyzed reaction, and the Lossen rearrangement requires a base. Okay, and yes, you will see Lossen is entirely different. Acidic catalyzed reaction of hydrozoic acid with carbonyl compounds which undergo rearrangement, extrusion of nitrogen to give you amine, nitrile, amide, or imine depending on the nucleophile. Okay, as well as your carbonyl molecule. So let's say you're starting with a simple ketone molecule. Okay, let's say we're starting with a simple ketone molecule. What are you supposed to do? In the presence of acid, the ketone is going to be protonated. The ketone is going to be protonated like this, and then the azide is going to attack. The N3 minus is going to attack over here, and you get OH R. I have deliberately kept the same these two R groups same, so that you don't have to first think about it, which is going to migrate. First, just see the mechanism. Okay, so let's say we have this form of the azide. Okay, the minus charge is going to fall up in this way, and as you can see, what is the intermediate that we will have in the presence of an H plus? This is going to become the oxonium ion, and I'm just removing the OH group. So you are going to get something like this: double bond N, all right, a single bond N, triple bond N, positive. Okay, I have removed water from here, minus H2O in the presence of the acid. Okay, now what is going to be your product C? The nitrogen gas has to eliminate over here, right? So what will happen next? You are going to, let's say, do the migration of one of these alkyl. We will think about it later who's migrating, but yes, the alkyl migration is going to give you an intermediate like this. All right, positive charge on nitrogen. This is your intermediate that you're getting. Okay, now depending on what is your nucleophile, let's say we are having water as nucleophile. Okay, So what is that definitely going to attack on this carbon? Yes. And what do you get? You get OH, double bond, N, H, and R. Still a positive charge. So you are going to do the tautomerism. You get the N substituted amide, right? This is what you get, N substituted amide, right? Okay, this is your product. So this whole reaction, this one, Schmidt rearrangement, does not have the isocyanate formation as you have seen till now. And if you are taking the ketone, it will not have the isocyanate. If you are taking the acyl azide and everything, yes, in the presence of hydrozoic acid, it might have. Okay, so it is going to have the intermediate, which is very, very similar to that of the Beckmann rearrangement. If you have seen the rearrangement, you will know it's also going to give you a similar intermediate, right? Yes. Now let's see an example of the same rearrangement. Now, ketone molecule, sodium azide acid present. So first of all, OH and azide. Let's say I'm writing it directly. I'm writing this directly, okay? So in the presence of an H plus over here, this OH is going to leave and the nitrogen is going to push it away. Alright, this is your molecule now. Positive charge on this nitrogen. Okay, very well. So this nitrogen has to leave, the nitrogen molecule has to eliminate, which bond is going to migrate. This is obvious that your ring is a better migrating group as compared to this carbon. So let's say this carbon is migrating, the bond is shifting directly, and you have minus N2. The ring is now going to be a 7-member ring. Why? Because one bond has migrated, okay? And the positive charge comes over this carbon. Very similar to what you get in the Beckmann rearrangement. Alright. So your product, I'm directly writing the product. First of all, you'll get a OH over here and then you will do the tautomerism. So I am directly writing the product. You will get this kind of a N substituted amide. Okay. Or a lactam. Lactam is a cyclic amide. Okay. So you might be asked this question and you might be given two options, which is the major product, or let's say you might be given four options, which is your major product and which is minor, and let's say you are having both in some quantity, right? So you're not going to fall for it. This is not going to be your product because it is going to form when the less substituted carbon migrates. Okay, you don't want to do that, so this is absolutely not your product. Okay, this is going to be the major product. All right, let's see. Last reaction for today is Lossen rearrangement. Okay, so guys, again, very important, but how can you differentiate? Because here you have this hydroxamic ester group, right? Activated hydroxamate. Okay, so Lossen rearrangement involves the generation of an isocyanate via thermal or base mediated rearrangement of an activated hydroxamate, which can be generated from the corresponding hydroxamic acid. All right. So, thermal or base mediated. We will see examples of both. So, first of all, let's say I have taken the hydroxamate over here directly, right? The OH minus, what is it going to do? There is a base. We require a base in this reaction, okay? We require a base over here, and that gives you the isocyanate. Once the isocyanate is formed, the fate of the product depends on the nucleophile. Okay, that part you can handle. Yes, so let's see what is this reaction. OH minus is going to attack over this proton. This proton is being removed from here, and then you are having a negative charge on the nitrogen. What will happen? The negative charge on the nitrogen, guys, once again, you can just remove this whole ester group and you can get the nitrene, but we can just directly write it like this. The R group is going to migrate on nitrogen, and now you remove this group. Okay. Yes, now if you remove this group as it is, you're getting the isocyanate plus RCOO minus, carboxylate. Okay, now you do the same thing. If it is ammonia, if it is ethanol, or if it is water, you are going to get different products that we have already discussed. Okay, so this is your Lawson rearrangement starting from the activated hydroxamate. Okay, let's also see a reaction. So this was the reaction for base mediated rearrangement. Let's see a thermal reaction. So here, guys, so yes, everyone, here you see that you don't have a proton on the nitrogen, you have the same hydroxamate ester, right? You are having a base also, but you don't have a proton, and this is your thermal condition. You have benzyl. All right, benzyl alcohol is your base that you have, is the nucleophile that you have. Okay, so what can you do about it? Yes, try this out by yourself and then I'll discuss. So, when you see that there is a tertiary butyl group over here, you can directly move the arrows in such a way that the OMS is going to leave. You know that mesityle is a good leaving group. All right. See, guys, I have to write the nitrene over here because directly I cannot write all of the things, all of the arrows cannot be written right on the same molecule. So I have to write the nitrene. So sometimes there are evidences that nitrene is formed, sometimes they are not. Okay, so I have to write the nitrene because I just cannot write the bond falls over here and then this group also migrates. It will be too uh confusing. So now let's use this electron density and write this part over here. All right, so now you have the isocyanate in this way, right? And who is your nucleophile? PH CH2OH, benzyl alcohol, right? It is going to attack over the carbonyl CH2PH, right? So this is your product of the whole reaction, right? Very, very simple. Lawson rearrangement is also very simple. You just have to figure out that this is your rearrangement going to take place. This is your thermal condition, and the previous reaction we have done for the base mediated reaction. Okay, so you usually see the base mediated reaction, but here I have also shown you thermal possibility. Very important to figure these things out. Why? How is the reaction driven forward? The reaction is driven forward entropically. CO2 eliminates, mesityle group also eliminates, tertiary butyl, this is your tertiary carbocation which is also stable, so that is why the reaction can move onwards in this direction. Okay, all right, guys. So we have studied very important name reactions today: the Hoffman, the Curtius, Schmidt, and Lossen. In the Hoffman rearrangement, it's your degradation reaction or rearrangement. Both the reactions are possible. Curtius takes place in the presence of heat or light. Okay, using the acyl azide, and Schmidt rearrangement takes place by the use of by the use of HN3, that is your acid. All right, that is your, alright, I just forgot the name of the acid. Hydrozoic acid. Okay. By the action of hydrozoic acid on the ketones, and this is going to give you a similar, okay, remember this thing also, it's going to give you a similar intermediate as the Beckmann reaction, not the isocyanate. Okay. And yes, Lawson rearrangement is hydroxamate ester in the presence of thermal or base mediated rearrangement, right? Okay, guys, so we have done 70 name reactions. I hope that you are revising the previous ones also. If you are not, please share with your friends as well. And if you have not yet subscribed to the channel, please do, so that you can get all the important videos that I am sharing with you. All the important content you are getting on time. So yes, guys, bye everyone. I will see you in another such video.